Hello everyone. Note down axis pressure. It's a water drop or drop of any liquid whose surface tension is S. S is the surface tension. Radius of this drop is R. Inside the drop, pressure is P internal. And in the outside region, pressure is P external. Inside P internal, outside P external. Our aim is to find P external minus P internal. Delta P, which is called axis pressure. Now, before we develop this, remember this result. Suppose we have a hemispherical shell. It's a hemisphere. And everywhere outside pressure is P. Let's call it P naught. And this P naught is same throughout. This radius is R. It's a hemispherical ball, placed upside down in this form, and in the outside region pressure is same. So all this pressure is pushing this thing downwards, and these are the forces which will act on it. Anywhere you go, force will be acting normal to the surface. And for a sphere, all these forces will be pointing towards the center. And when you take components of these forces, the directions are always such that force is acting towards the center. They are normal reaction forces, and normal reaction is always perpendicular to the surface. So if you have a surface like this, so this is the spherical surface, and all around pressure is same P naught. So that pressure is pushing this ball like this. from all the directions. And these forces, at any point, if you look for the direction of force, that direction will be towards the center. These components will be cancelled coming from this side and coming from this side. These components will survive. And remember this, that net force, total force, if you are looking for, will be P naught multiplied by pi r square, provided P naught is what? Same. If outside pressure is same, then total force will be this, and in this case you can see that direction will be what? Downwards. So this is a result. Note down this. And it's not about this spherical shell. If you have a cone, look at this also. Suppose you have a cone and again pressure outside is what? Uniform, P naught. If we need total force acting on this cone, this will be the direction of that total force. Call it F, and remember this F will be P naught multiplied by this area, the base. You don't have to go for lateral surface area. Instead, go for the base area, which is again what? Pi r square. The concept is valid for any type of shape. If you have a hut shape, on this, you don't have to worry about this and this. Just look for the area of the projection. How do you find area of projection? How do you identify projected area? Imagine if you throw light from this side and you hold a screen over here, then the shape of shadow which you see, light coming from this side and you have the screen, what type of shadow do you expect? Circular. Light coming from this side, screen, what type of shadow? Again a circle. What is the area of the circle? Pi r square. So this pi r square is the area of that projected surface. Note down this as a side result. You can always prove this thing. At any point, find out the surface area. We have done this thing with Pascal. So you can see small areas. Any small area, take it like this. This area will have two components. Although area doesn't have components, it's a scalar quantity, but you can see Pascal's law, and we use the concept of displacement also as a trick. So this is concept of vectors for area as a trick. So if this is the surface at any place, this place, this place, so this surface will have two components, vertical and the horizontal one. So at any place you go, any place on this if you are present, say this much, very small portion. This small portion will have two components, one horizontal, one vertical. Similarly, this will have two components, one vertical and the other one horizontal. If I need force on the curved surface, I will say that find out force on this and find out force on this. Find out force on this, find out force on this. Go and see Pascal's law and you will find this. This and this, they are cancelled. Look at this. All these are what? Projections. Projections of this much. Projection of this area over here. Projection of this area over here. And if you go for the entire curved surface, what is the projected area which you get? This much. So in one line you can use this thing, provided outside pressure is what? Same. This pi r square, remember, is the projected area. Put down this, note down this, and if you wish you can use this as a side note, the way you arrive at this concept. Write down this point with this, that concept of projected area should be used only if pressure is same everywhere. Concept of projected area should be used only if pressure is same everywhere. Now, look at this drop. Let's draw a free body diagram of two halves of this one drop. One drop, split it into two halves. Just a free body diagram, you're not splitting the whole thing. Free body diagram. From this side, force is coming F1, which is P external into pi r square. This is the internal part. From the internal side, force is coming F2, which is P internal multiplied by pi r square. Inside, everywhere pressure is what? P internal uniform. So that internal pressure is pushing this hemispherical portion in this direction with the force of F2, that is given by P internal into pi r square. At the same time, effect of surface tension takes place over here at the boundary which is touching this second half. So the first half is touching the second half like this. Surface tension is effective only for what? Surface. So this portion where I have shown the forces in blue, these are the forces coming because of surface tension, and this force due to surface tension, let's call it F3, is S multiplied by L. That's how we define surface tension. What is L? 2 pi r. where r is the radius of the drop. So this half is pulling this half towards itself with a force of S into 2 pi r. Internal portion is pushing this in direction shown by F2. External medium, whatever it is pushing this in this direction shown with F1. And ultimately, the drop is in equilibrium. If this thing is in equilibrium, then you will say what? Concept of free body diagram. You have three forces acting on it. F1 in this direction, F3 also in the same direction, being balanced by what? F2, which is acting in this direction. F2 is shown by the black arrow. F1 is what? Normal reaction force towards the body. F2, normal reaction force towards the body. This F3 is surface tension force. What is tension? That acts away from the body. Away from the body. All the blue arrows collectively, अगर इनका सारे के सारे blue arrows को आप add कर देते, तब जो total force बनता, that total force is what? F3. About these values, F2, F1, F3, and you get, what is F2? P internal into pi r square minus F3. Shift this F3 over here. F3. What is F3? Oh wait, not F3. Shift F1 basically. F1. This side. This was P external. P external. So this is F2 minus F1 which is equal to what? F3. F2 is P internal into pi r square minus F1 is P external into pi r square, and this is equal to what? F3, which is S into 2 pi r. S into 2 pi r. We are interested in, make it P internal minus P external. There is more pressure inside. P, do the correction, P internal minus P external. P internal minus P external, pi cancel, r cancel. This is coming 2s divided by r. Pi gone. R gone. Shift the r over here. This becomes 2s upon r. For a drop, internal pressure and external pressure, if you go for the difference of these two, will be equal to what? 2 multiplied by surface tension divided by r. Note down this. Now, this was access pressure for a drop. But suppose if instead of a drop, we have a soap bubble of radius r, surface tension S. Now let's see how many of you can give me access pressure for a soap bubble. Write down the adding access pressure for a soap bubble. This time it's not a drop, it's a soap bubble. What do you think will be the change? It's very easy thing. In just 10 seconds you can guess that. Excess pressure for a bubble. To be precise, hollow sphere. So what do you think change will be? Good. Some of you have already answered it. Very good. It's a very easy thing. And we have discussed this part previously in one of the lectures. If it's a soap bubble, then it has two surfaces. You can draw a separate free body diagram, separate figure, everything. I'll do that in this figure only. So there are two surfaces present. There are two surfaces present. Inner and outer. And it's very thin, and therefore we'll take the radius as what? R only for both. Inner as well as outer. Concept of F1, concept of F2, that is exactly same. Regarding surface tension force, there are two surfaces present, and therefore this is the correction. You will write 2SL. Multiply the whole thing with 2. There are two surfaces. Both surfaces are being pulled by a force of SL and SL. Together 2SL. So this is 2. This is 2. Multiply this thing with 2. Multiply this thing with 2. And you get 4S divided by R. So excess pressure for a soap bubble is 4S divided by R. Note down this. This time we have a soap bubble. You can show an inner surface. I hope you can understand what that figure is. I've shown you that thin portion. Now answer this. Which has more internal pressure, drop of water or a bubble of water? You made a bubble of water, both are of same size. Let's not call it soap bubble because soap will change the surface tension. We have a drop of water and we have a bubble of water only of same size, same radius. Which one will have more pressure inside? What is the answer? You can expect these type of short answer questions. Look, what I'm asking you is this. This is the drop. Pressure inside the drop is P D. D for drop. Outside external. Same size bubble. Pressure inside is PB. Pressure outside is P external. Well, outside pressure is what? Same. They are both in the same surrounding medium. So what is P internal minus P external? 2S upon R. Water, that means they have same surface tension. What is PB minus P external? 4S upon R. Four S upon R. From this, subtract this. So when you subtract from this, subtract this, px cancelled. 4s minus 2s is what? 2s. So pressure inside a bubble minus pressure inside a drop of same material, same size is 2s divided by r, and for us PB is greater than PD. And you have the value of that also, 2s upon r. If you find pressure inside a drop, pressure inside a soap bubble, then pressure inside a soap bubble is greater, and the difference is 2 into S divided by R. Note down this. Now answer this next question. We have two bubbles, one large, other one small. Which one will have more internal pressure? Larger bubble or smaller bubble? Answer this. Which bubble will have more pressure? A larger bubble or a smaller one? P in minus P out. Out means external. P in minus P out is coming what? 4S divided by R. P internal minus P external is coming what? 4s divided by R. You have a larger bubble. Actually, radius is capital R. Smaller one. Look here. As you increase the radius, as you increase the denominator, your P out external is same for both of them, and therefore P in should decrease. A straightforward thing, कुछ खास या special type का नहीं हुई. You're using simple formula. We are increasing R, and therefore P in will be less. So let's say pressure inside is PR, and pressure inside is PR. The answer is that PR is less than PR. Smaller bubble will have more pressure inside. Go down like this. Well, everybody has answered correctly. Good. Now, this is something which you can yourself, kind of experiment which you can conduct yourself, and the way you can conduct it is something in this form. Note down this fast. They ask you a question in this form. Suppose you connect a tube between larger and smaller bubbles. A large and a small bubble. The question is, which one of these two is going to inflate? Whose size is going to increase? Answer this fast. If a large and a small bubble, they are connected by a tube, then whose size is going to increase? Smaller one or larger one? Good. Look here, everything is on the board. जो छोटा वाला है उसके अंदर प्रेशर क्या है? ज्यादा. And you know that air moves from, air is inside, it's a bubble, air is inside. Air is going to move from high pressure zone into low pressure zone. So draw a separate trigger. The moment you connect these two, flow of air will be like this. From high pressure zone, you can write like this, high. Inside pressure, high. From high, air is going to move to low, and therefore size of larger one is going to increase. And you can do this experiment yourself. Take two balloons, blow air inside, one of larger size, other one of smaller size, join them together and see what happens. This is something which you can conduct yourself, a very elementary experiment. And everything is coming from this simple effect of what? Surface tension. Draw a separate trigger. This is the high pressure zone, this is low pressure zone. And once you connect it, air is going to flow from high to low. One more interesting thing which you can see again yourself is, suppose you make you take a soap solution and you make bubbles, and you must have seen that when you make these bubbles and all, तो कई बार वो आपस में चिपक जाते हैं. तो अगर आपस में दो बबल चिपके हुए हैं and are of not equal size, दोनों के साइज अलग अलग हैं, अगर चिपके हुए हैं, that means they have a common surface. So the question is, common surface will be inside which one? Inside the larger one or inside the smaller one? Answer this fast. The question I'm asking you is, you have a soap bubble, larger one, smaller one. So this is the common surface. Common surface will be inside smaller one, or common surface will be inside the larger one. A question like this can be asked in any examination. Well, everybody is answering smaller one. क्या हो गया भी आपको? क्या हो गया है आपको? सामने अभी आप बता पा रहे थे, air is going to flow from high zone to low zone. मैंने ये क्वेश्चन पूछा और आपकी हवा निकल गई. अगर आपके पास एक डायफ्राम है, let me draw it much larger so that you can see it clearly. This is the larger one. This is the smaller one. Imagine a diaphragm at the junction, a sheet, a thin sheet. This is high, this is low, and you have a thin sheet present here. So in which direction this thin sheet is going to bulge? This is high pressure zone, this is low pressure zone, and therefore the common surface will be inside the larger bubble. This L is for low pressure, and the common surface shown in red will be inside the larger one. L for low pressure, let me write low, high, and this is your common surface. The common surface is what? Inside the larger one. And everybody is writing a smaller one. Any confusion, or is this thing clear? So all those who wrote smaller, 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 is the concept clear? Good. And this is an experiment which you can again do yourself. Make these bubbles and see which one has the common surface. Now there is a homework for competitive examinations. Assuming common surface to be a hemisphere, it's not necessary that it should be a perfect hemisphere, it can take any shape. Assuming this common surface to be a hemisphere, if radius of the larger one is r, radius of the smaller one is small r, then find out radius of the common surface, which is radius of the hemisphere shown in red. Let's call it r naught. So what is R naught? R naught is radius of this common surface. You need to find R naught in terms of R small r. This is for competitive examinations. Things like which one will have the surface inside, larger one or smaller one, you can expect it in any examination. Now write down angle of contact. What is the angle of contact? आपने इस तरह की चीज देखी होगी that in a glass, if you have water, then top surface is not like this. This is not the correct profile of top surface. Correct profile is this. This is the correct profile. At the side where liquid touches the beaker, it has a concave surface. And if you have seen mercury inside a tube, then that mercury column, its top surface looks like this. If you can see anywhere mercury in a tube, then top surface will look convex. This is the correct profile for mercury. This is the correct profile for water. These surfaces are not flat all over. The place where liquid touches the beaker wall, it can make concave or convex shape, which will be explained by the concept of angle of contact. This is what we are interested in. Now look at this place. हमने एक बीकर के अंदर लिक्विड फिल किया. Let's talk about water or anything, it doesn't matter. Look at the side portion, the corner. At the corner, I hope you remember force is in this direction. A molecule deep inside, force was 0. At the top, it had a downward force. At the corner, force is in this direction. What is this force? All the molecules, the force which they exert on the molecule, which is right at this position, at the corner. All the liquid, you can say, although a molecule at this place doesn't get any force from a molecule in this region. The force is coming from a very small area. So, any molecule at the corner is being pulled inside by a force, and the force, you know, this force is nothing but cohesive force. Force between same type of material. All the water molecules are attracting this water molecule at the corner with a force which will be called F cohesive. gravity is pulling this downwards. That's your mg. Walls of the beaker or the container inside the liquid is inside, is pulling this molecule towards itself, and this force is called adhesive force. Force between different types of molecules is what adhesive force. Force between same type of molecules is what cohesive. These are the three forces which are acting in this region. Adhesive coming from walls. And why is the force horizontal like this? Look here. This is a wall. This is the molecule. Water molecule over here. Free body diagram. This is the wall. Glass wall. The glass wall also has what? Several molecules. And these molecules are pulling this one towards itself. So if you have a force like this, you know that vertical components will be cancelled, only horizontal components will survive, and therefore this. But force coming from the water is not in the horizontal direction, because at the corner there is, if molecule is at the corner, there is no liquid present in this region. Liquid is present only in this region. And that's the reason you show adhesive force in this direction, cohesive force at some angle, and mg downwards. This is true for any liquid. Now, अगर हम बात करें वाटर की, तो आपने एक चीज नोटिस की होगी कि अगर हम वाटर ड्रॉप्स को एक ग्लास सरफेस पर आप डाल दें तो उससे चिपका रहता है वो। पानी लो, पानी की कुछ बूंदें ग्लास के ऊपर फेंक दो, ग्लास सरफेस पर, तो उससे चिपक जाती हैं। चिपक जाने का मतलब क्या है? यहां पर F adhesive is greater than F cohesive. Force between glass and water is the dominating force as compared to force between water molecules. This is for water and glass. For water and glass, force between water and glass is greater than the force between water and water, force which is cohesive. Whereas if you talk about mercury, मर्क्यूरी में आपने क्या नोटिस किया होगा? पता नहीं आपने किया होगा या नहीं किया होगा, because nowadays mercury is not easily available. If you try to stick mercury to a glass surface, it doesn't do that. Mercury and mercury, it connects to other drops, makes a larger volume, but it doesn't stick to the glass surface. So if you try to stick mercury on a glass surface, that's not possible. In other words, you are saying that F adhesive, this is a F adhesive is less than F cohesive for mercury. इसका और इसका मतलब क्या है वो देखना. If I say that F adhesive is greater than F cohesive, if F adhesive is greater than F cohesive, then resultant force will be in this direction. This is resultant force shown in blue. F total. Resultant of what? Resultant of these three forces shown in black is what? The blue one. This is for water. For mercury, adhesive is less than cohesive. This is the dominating one, and therefore resultant of these three will be somewhere in this direction, shown with red arrow. And I hope you can see both these arrows clearly. This is your F total. Red for mercury, blue for water. Up. Notice this thing. Suppose you have a surface which can rearrange itself. Liquids, they always rearrange their shape and size. Shape basically. If a liquid is under some force, then you can notice one thing, that liquid will take a shape such that force is perpendicular to the free surface. Listen again. We say that liquids cannot withstand shear forces, tangential forces. What does it mean? If you have a very hard surface, look at this duster, the wood, it's a hard surface. If force is coming at this angle, then I hope you can see the separation, the gap between this and the inclined portion of the duster. A solid, it doesn't deform easily if you apply a force on it. But now look at this. If you can, I don't know it would be if you can see this thing easily or not. If you have something which can easily deform itself and a force acts on it, a little bit difficult for you, but you can easily visualize this thing. If on this soft thing a force acts, then I hope you see the gap. But if I continue pressing it, then I can easily deform it. And when that deformation takes place, something like this happens. So this is the surface and a force is coming this way. Then this surface for a liquid will take this shape. It will become what? Perpendicular. Why? Because if surface is held like this, then this force has a tangential component which is called shear, and liquids cannot withstand tangential forces, shear forces, but liquids can easily withstand longitudinal compression. Take a liquid in a tank, put a piston on top, try to push this piston down. You cannot do that because liquid is what? Incompressible. We say that liquids can easily withstand what? Compressive, longitudinal compression. Then do what? Take your hand inside, remove the piston, take your hand inside and try to move the hand horizontally, producing what? Shear forces. It is very easy for you. You can do that. That means we say that liquids cannot withstand what? Tangential. We'll write all these points, don't worry. Now, the moment I say that liquids cannot withstand tangential forces, this is the force which is for mercury, and this is the force which is for water. Top surface should deform under these three forces and should take that shape which is perpendicular to these resultant forces. क्यों? क्योंकि ये जो फोर्स है, अगर सरफेस अभी भी इसी तरह से है, then this force has one horizontal component, and the horizontal component is the tangential force, and liquids cannot withstand these tangential forces. So this liquid surface should reshape itself such that this force only provides normal forces or forces which are perpendicular to the surface. That means for water, यहाँ दिखा दे रहा हूँ, देखना. For water, your surface should become like this. Why? Because this is the force. It cannot be of this type. It cannot be of this type. Not allowed. It should be of this type. This is allowed. This is the top surface. Join it. Do the same over here. This is for water. Now let's talk about mercury. For mercury, force is the red one. Force is in this direction. So this is the force, and therefore surface should be perpendicular like this. Continue this. That's for mercury. If you understand, I will explain angle of contact and all, what is angle of contact in this. But if you understand the reason behind concave and convex profiles, then write down yes in the comment box. If you understand the whole thing, and also note down everything. Blue one is for water and red is for mercury, and then show like this. This is your F total. This is your F total. If you understand this, then write down yes in the comment box. Good. And this, you don't have to find any soft surface or things like that. Hold your pen, the flat portion of pen, against the soft portion of your palm. Now, as you push your pen into the palm, you will find that it deforms and becomes parallel to the base of the pen. Becomes parallel to the base means becomes perpendicular to the direction of force. Now write down these few things. Liquids cannot withstand shear forces. Liquids cannot withstand shear forces, inside the bracket tangential forces, but they can easily handle longitudinal forces. Inside the bracket normal reaction forces. This is the reason why, top free surface of a liquid, gets deformed, where it meets the side walls of a container, where it meets with the side walls of a container. Well, it's not about side walls of a container, it's happening everywhere. Why is the top surface horizontal? You know, why is the top surface horizontal? Because force is only what, mg. And that downward cohesive force. So forces are only what, vertical. If forces are vertical, then surface will be like this. And those of you who remember concept of pseudo, I'll give you another example of the same concept. I hope you remember I had asked you a question like this. We have a beaker filled with water, is accelerated in this direction. If you accelerate this thing in this direction, then top surface, I asked you, it becomes this or it takes this shape, type 1 or type 2. I hope you remember this profile. Now, let's answer this. Those of you who are comfortable with pseudo forces. If you are not, go and watch the lecture. If this is accelerated with A, take an observer, hypothetical imaginary observer, ask him to sit inside the beaker itself. And once he is inside, what he says, a pseudo force is present in this direction. Pseudo force. ये ऐसे ही इंटरेस्ट के लिए बता रहा हूं, समझ में नहीं आया तो परेशान मत होना, ये काम का था. mg is acting downwards. If you have an observer who is sitting inside, he says that there is a pseudo force in that direction. What is this pseudo force? अगर आप कार में बैठे हैं, कार एक्सेलरेट हुई तो आप पीछे की तरफ फोर्स फील करते हो, that is pseudo force. आप मतलब आप, वो आदमी जो कार के अंदर बैठा हुआ है, he is a non-inertial guy, he has to apply pseudo force. क्यों? Go and see the lecture. So, for him, these are the two forces, and what is the resultant of these two forces? Resultant of these two forces will be in this direction. F total, shown by blue thing. तो जैसे ही टॉप F total इधर आया, लिक्विड की प्रॉपर्टी क्या है? शेयर हैंडल नहीं कर पाएंगे भाई. ऐसा बन जाओ कि फोर्स से 90 पर shape हो जाए. And therefore, I hope you remember, answer was this, and we had found tan theta as A upon G. अगर आपको सूडो फोर्स का आइडिया है तो आपको ये चीज समझ में आई होगी. जितने लोगों को ये समझ में आया हुआ है, राइट डाउन यस इन द कमेंट बॉक्स फास्ट. नहीं आया परेशान मत होना, सूडो का कॉन्सेप्ट है. टोटल दिस. Now, let's talk about angle of contact. This is your, this is water. Draw a tangent on the curved portion. That's a tangent. Use an arrowhead such that arrow is acting away from the liquid. Draw another tangent on the side walls. Another tangent on the side walls. Find this angle theta. This theta is angle of contact. Let's talk about Mercury. Draw a tangent on the curved surface, put an arrow away from the liquid. Draw another tangent on the side walls away from the liquid. Away from the liquid, away from the liquid, away from the liquid, away from the liquid. Find this angle, theta. This is your angle of contact, which gives us a very elementary question, but very important question. If, let's see how many of you answer this part fast. If F adhesive is greater than F cohesive, don't have to see anything. If F adhesive is greater than F cohesive, then angle of contact will be acute or obtuse. Fast. If F adhesive is greater than F cohesive, then angle of contact will be acute or obtuse. Answer this part fast. क्या पूछा मैंने? If F adhesive is greater than F cohesive, तुरंत हमने दिमाग में लगाया F adhesive between walls and liquid, water चिपक जाता है. इसका मतलब किसकी बात हो रही है? वाटर की बात हो रही है. वाटर के केस में F adhesive is greater than F cohesive, and in that case angle of contact theta is an acute angle. और अगर बात किसकी हो रही हो? मर्क्यूरी की, which is F cohesive is the dominating thing. F cohesive is greater than F adhesive, then your theta is an obtuse angle. If you understand the concept of angle of contact, then write down yes in the comment box and then you can leave. Thank you very much.